And looking at measurements, so we're now going to bring in a little bit of quantification. So first, a basic idea of what we're trying to do within science is we take measurements, and it is the acceptance of those measurements by others that allow us to progress forwards with both our observations and kind of conclusions from those. So for a measurement, it's really composed of sort of two things. You get a number, and then you get a unit. Both things must be included there, otherwise the measurement doesn't make any sense. For instance, if I say I am 6 years old doesn't make any sense. I'm a size 6. For women, you might be like, he's probably not a size 6. Okay, I'm 6 feet. Okay, 6 feet tall. So the meaning that comes from that number drastically changes when we change that unit. Okay? One of the things that's going to add to our understanding of science is it's not just the number and then whatever that measurement unit is, but also the substance. What is the substance that you are measuring? So if I just say 6 feet could mean I'm 6 feet. It could also mean my wife is 6 feet. It could mean the closet that I'm in has a width of 6 feet. So all of those things carry different meanings and conclusions, right? Because you might be like, well, dang, his wife is tall, or dang, that's a tiny little hole that he's in, right? All of those interpretations come because you're changing some aspect of that information. So whenever you write something down, you should be focusing on the fact that there is a number, a measurement unit, and then a substance unit. So you really get 3 pieces that get attached to it. Right? And you'll see, even as I go through and talk about things, will make mistakes and not reference all 3. But try your best to make sure you're referencing each of those 3 pieces. The next thing are what are the things that we'll take measurements of. So you get distance or length, mass or weight, depending on if you want to use a physicist's definition or not. We don't care in this class, so you can call it mass or weight. And then volume and time. So there are common accepted units for those, and depending on where you're at, you get different references of those units. So you may need to change those depending on the environment you're in. Okay? For the most part, the environment that we're going to talk about is science, and again, for the most part, scientists use the metric system to describe those. Okay? At this point, I don't really want to get into what those units are. I lied. I forgot. This was the slide we're going to move to. What are those units of the metric system? Your table has a nice little, or your textbook has a nice little table that gives you those basic units. Okay. It is important to note that all measurement systems are complete arbitrary invention. Okay? This is why we get inches. This is why we get feet. Okay? We can still run and build things based off of those measurements, but everybody else has to use that same measurement, otherwise it doesn't work. So for our class, our primary measurements for length are going to be meters. For mass, we'll use grams. For volume, we'll use liters. And for time, we'll use seconds. So those are what I like to reference as a core unit. Okay? And that core unit term will make a little bit more sense, maybe even later in this lecture. So a core unit, and we can address it right now. Have you heard of, say, a kilometer? Okay, well, a kilometer is km. Okay, well, the core unit is that m, meters. The k in front is an application of that core unit, is a multiplier. So when we talk about that core unit, you're looking for that m, g, capital L, or s, and there'll always be some kind of multiplier, if you will. Not always, but there's usually some kind of multiplier in front, okay, that modifies that to be either bigger or smaller. Yeah. So how do we do measurements? So we already addressed the number and the unit, but now how do we actually take an actual measurement? So it's easiest to do with length, okay, but most of our measurement systems are some level of analog. So if we look, where is that arrow located? Kind of a challenging question because we might have to go through and actually count out each of those pieces. But if we went through and did it, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Those would be decimals. So a potential answer could be 0.75. Right? And I wouldn't be surprised if somebody guessed that. But how about 0.6? Okay? Or even 6.6? You might say, well, that's entirely wrong. That's not a valid description of where that is, because the 0.6 would then be somewhere over here, and our blue arrow isn't there. Right? So the measurement gives us some information that allows us to exclude this as a valid measurement. Right? Well, how about 0.76593221? Is that a valid measurement of where that arrow is located on there? And for those of you complaining about units, I apologize. Like I said, I screwed it up already. That measurement, we don't have the precision in this demarcation of our ruler that allows us to report those pieces of information. So really all we're doing is the same thing that we did with the 0.6. The 0.6, though, the device could tell us that this was wrong. But now for all of these numbers, the device isn't telling us we're wrong, it's telling us that we are guessing. Right? And that becomes a problem. Right? So when we're looking at science, we want to report exactly what our device tells us. We don't want to report patently wrong things, but we also don't want to provide so much information that we're just making stuff up. And defining that line becomes a little bit challenging. So the general rule is written up there. Provide your obvious digits, and then you get one guess as a decimal point, one extra guess as a decimal. Right? Or, and I shouldn't say decimal, one guess digit. We'll see why that is here in a second. So for that blue line, 0.75 is a fantastic guess or a measurement of this. We know we haven't achieved the 1 in our ones place. We know we have cleared the 0.7 in our tens place. We don't know anything about that next point. We know we haven't achieved the 8 yet. That's still back here. Okay, so we are somewhere between 0.7 and 0.8. Now we're taking a guess. And our guess is that we're roughly right in the middle, so we're saying 5. But it could have just as easily been 4 or 3. If we threw on another guess, okay, this is now using the information, or really what we're using to come up with these guesses is the information we have in front. And in the case of the 5, I'm using the fact that that 7 is a guaranteed. That's a certain obvious digit. If I look at the 3, I'm relying on the previous information. The previous information was a guess. So that 3 is a guess on a guess, which equals a guess. Okay, for the purple one, it was a guess on a fact. That's an educated guess. That's allowed. But don't start guessing on guessing. I did make reference that it's this one guess digit, not decimal. Okay, what do I mean by that? Well, let's advance this a little bit further. What happens if we now change this to 1,000? Okay, where is that line now? Okay, so let's walk through it. These again were 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are now our hundreds place. So if we were to look at this as a number line, we are guaranteed, whoops, here's a number line. We'll just give it a bunch of numbers. And I'm going to drop a decimal point there. I'm guaranteed that that is a 0. Okay, for that matter, everything up here is also zeros, right? And then I know I'm larger than the 700, but smaller than the 8, so I know this has to be a 7. Okay. The next piece of information, Okay, I'm going to use that 7 because that's my last demarcation. I get one extra guess digit. I'm going to guess 4. Okay, what do I do with the rest of these spots? Okay, and that's the point of the measurements. I can't specify any information about them. I don't know that they're a 1 through a 9. I don't have any meaning about them. So what I could do is invent a symbol, and I'll invent that symbol question mark. So if I was to write out my measurement, it would be 0.00000000007 question mark decimal point question mark question mark question mark question mark question mark question mark. You get the idea that that now becomes very difficult to understand what we were actually talking about. So what somebody had the brilliant idea of doing is saying, well, the zeros out here I don't need to show because they're just zeros. So I'm just going to start with my 7. Okay? I know that 7 needs to go in the hundreds place. Okay? So I could do 74 question mark. But is that a 74 question mark or is that 740 question mark? Well, 740, so what I'm going to do is put a 0 here. Is that 0 that I know that it's a 0? Or is that 0 really just as a placeholder to ensure that I place the 7 in the hundreds place? And this is now the birth of our significant digits. Okay? We end up using the 0 to mean 2 different things. The 0 means not a digit 1 through 9. It also means, hell if I know. The problem with that is it's the same symbol, right? So we have to be very careful about how we represent our numbers to ensure that we get the proper reading so that when I look at a number, the instrument's accuracy carries across. And that's a challenging thing to do if you don't know the rules. That's why we have rules, right? So what are those rules? Those are what are known as significant digits. Okay? Textbooks and the internet, everything is going to go through probably about 5 or 6 rules. There isn't a need for 5 or 6 rules. The only reason there's a need or a list of 5 or 6 rules is because someone created a rule and then realized it didn't cover everything. So instead of fixing the rule, they put tape on it. Right? It's like you're in a boat, you find a hole, so you put glue in it. Another hole pops up, you put more glue in it. Eventually, you need to rebuild the freaking boat. Right? That's what these rules are here for. Okay? So these rules work always. Not sometimes, always. That's why I would recommend you use these. You don't like my rules? That's cool. Use the ones that you find online. Interesting feature about those rules found in your textbook or online, they weren't created necessarily by scientists. They were created by the testing society in the US. When we moved to a system where we had to have standardized tests across the nation, we needed an absolute system to qualify our significant digits. Okay, so beside the point, how do we apply the rules? So first rule, 1 through 9, always significant. Okay, those are always important. There's no ambiguity behind it. If I say 1, I got 1 finger. If I say I have 3 fingers, I can't point to that and say I've got 1. I have to have 3. Okay? Where we run into ambiguity is what we had in the last example. Is the 0, does that mean not 1 through 9, or does it mean I don't know what it is? Okay? That differentiation comes in with the explicit placement of the decimal point. And for those people wondering, well, why couldn't we do it another way? We could use a number line, and you could specify the location of every single place for a number. That's an infinite number of places. You wouldn't be able to do it. This is why we use sig figs. Okay, so if there is no decimal point, then a 0 has to be controlled, okay, by significant digits. It's better to say significant digits instead of numbers, to the left and right at any place to the left and right. As long as there's a significant digit to the left and to the right of a 0, that 0 will be a significant digit. Okay? If there is a decimal point, then the 0 just needs to be preceded by a significant digit to be significant. Okay, so it just needs to be a digit to the left. So really all we're doing is left and right. No decimal point, left and right. Decimal point, left. Okay, so we've got 8 examples there. I usually ask this in class, have everybody go through and figure it out, and then we walk through the answers and talk about them. So instead, what I'm going to do is say, go through and figure it out on your own, answer this question. Okay, and now what we'll go through and do is we'll highlight the ones that typically students ask about. Okay, typically, hopefully it covers you. Okay, so let's take a look. Usually we get a question here, here. Where's the other one? I'm just going to say these two, but I could be wrong on that. Okay, I'm going to throw in these two real quickly because the difference here is that really nothing. They're both 2 significant digits, 1, 2, 1, 2. So why is this 0 shown here? Okay, this is just an artifact really of how we write. You're typically using a pencil because you make mistakes. If you make a decimal point with a pencil, sometimes it works out really well, but my hand isn't very steady and all those dots are showing up really well. Okay, but typically if we make a decimal point with a pencil, it disappears. So if I wrote something like that and said feet, I'd be like, well, 12 feet, that's an idea of a general room. No, that's not 12 feet. That's decimal point 12 feet. Okay, that's looking at the length of my thumb. That's a pretty big difference. Thumb versus room. Okay, so the decimal point is a really big deal. So if you're one of those people that lightly dots, you should use the 0 in front. The reason being is that if you get used to using that 0 and your decimal point is very, very light, you might look at this and be like, why did I write a 0 in front of 12? That doesn't make any sense. Oh, there was a decimal point there. Okay, that pause is just long enough to ensure that you actually use the number you're supposed to use. So back to the questions that you had. I used air quotes there that were awesome because you can't see that, but here we go. Let's take a look at, we'll call it our blue star. 1 through 9 are always significant. So 1 and 2, significant. That 0, okay, to the side, I have to look for an explicit decimal point. There is only an implicit decimal point. It's not shown. Okay, because it is only implied, I have to use rule 2. For that 0 to be significant, there has to be a significant digit to the left. Well, what is to the left of that 0? A significant digit, as seen by the underline. What is to the right? There's nothing there. That means there's no significant digit there, which means that 0, not significant, there are 2 sig figs. We move to the 1 underneath it, 1, 2. This time, it is explicit. Because it is explicit, I can use rule 3. Under rule 3, all I have to do is look to the left. That was a significant digit. Because it is a significant digit, I can underline that. That is now 3 sig figs. Okay? We'll call them purple. And whoops, that was supposed to be green. In green, if we take a look at the purple one, again, the 1 and the 2, there is an explicit decimal point. So I would use rule 3. Rule 3 says I need to have a significant digit to the left. What is to the left of that first 0? Well, nothing, which means not significant. To the left of the other 0, is there a significant digit? No, which means 2 sig figs. I move to the green one. I've got the 1 and the 2 again. First 0, I move to the left. Nothing, not significant. To the left of that other 0, I've got a 0 that was not significant. Last one, I moved, that's a significant digit, which means the 0 is significant, and I get 3 significant figures. Okay? The amazing thing about these rules is that they will always work. There isn't some weird loophole that you have to patch with a new rule. These rules work. Okay? So I would highly encourage you to use and apply these. If you want to, use and apply them and try and break them. Let me know when you break them. Okay? With that, we do have some other kind of weird things that kind of potentially pop up, because of course it can't be 100% straightforward. That was not supposed to advance. That was fun. If we go through and look at this, measurement versus exact. Okay. Distance, mass, and volume are only as accurate as the instrument measuring them, but are there measurements that don't require an instrument? For instance, if we look at the picture below, how many quarters do we see? Okay, hopefully, I know it might be small on your screen, you can always blow it up. You should hopefully see 7 quarters. Okay, so there's my number and there's my substance. How many significant digits in that number? Okay. Usually we'll hear people saying 1. Okay. So that means if there's 1 significant digit, a valid observation of those quarters could have been 7.1 quarters. You're following? No, it's not 7.1 quarters, it's 7.0 then. So it's 2 significant digits. So a valid observation would be 7.11. Well, I'm gonna add another 0 then. 7.111. Okay. Then what you should note is that if you're going to try and run this argument of I'm just going to keep adding zeros, I'm going to keep adding ones, making your observation of the number of significant digits wrong until you reach a certain point. Okay. You'll never reach that certain point, but there is a name for it. It's infinite. Okay. An exact observation has infinite sig figs, not 3, not 4, not 5. There's no number associated with it. It's an infinite number of sig figs. 7 quarters. There are exactly 7 quarters. It's an infinite amount of significant digits. Okay? So there are some measurements that have infinite sig figs. These tend to be not measurements, but observations or definitions. For instance, how many inches are in a foot? 12 inches, 1 foot. How many sig figs? Is it 1 because of 1 foot? Is it 2 because of 2 inches or 12 inches? Right? It's neither. It's infinite. That's an exact definition. Because it is defined as that, it has an infinite sig figs. Right? It is not a measurement. Right? Which is a challenging concept, but what you'll find is that it's not that big a deal. Okay, oh, dang. And with that, we are done with this lecture, and we'll look at the application of significant figures in the very next video.